So I'll start with announcements. Homework number 6 on chapter 7. I extended the due date to the 24th because of the weird outages Pearson's been having last night and today. So the homework number 6 for chapter 7 will be extended to the due date to Friday. Homework number 7 for chapter 8 is due on the 29th. And we have a lab on Wednesday. We should be finishing up chapter 8 today. So conservation of mechanical energy. We've been talking about mechanical energy. Mechanical energy is defined as potential energy plus kinetic energy. And using this definition, if you only consider conservative forces, you find that mechanical energy, potential energy plus kinetic energy is conserved. So mechanical energy final equals mechanical energy initial, or equivalent. Mechanical energy is a constant. So here, if you have a 55 kilogram skateboarder and they enter a ramp moving horizontally with a speed of 6.5 meters per second, and they leave the ramp moving vertically with a speed of 4.1 meters per second. Find the height of the ramp, assuming no energy loss to frictional forces. So remember that kinetic energy is 1/2 mv squared. Potential energy from gravity is mgh, or mgy, though in this case it will be h. And that energy initial equals energy final. So potential energy initial plus kinetic energy initial equals potential energy final plus kinetic energy final. So we can set this up. We have our initial velocity is 6.5 meters per second. Our final velocity is 4.1 meters per second. Our mass is 55 kilograms, and we're trying to find the height. So energy initial equals energy final. So kinetic energy initial plus potential energy initial equals kinetic energy final plus potential energy final. So that's 1/2 mass times velocity initial squared plus 0 equals 1/2 mass times velocity final squared plus mgh. So if we solve for height, first thing we can do is divide through everything by 1/2 mass. We get v initial squared equals v final squared plus 2gh. So v initial squared minus v final squared equals 2gh. So h is v initial squared minus v final squared over 2g. The height is going to be 6.5 meters per second squared minus 4.1 meters per second squared over 2 times g. 2 times 9.81 meters per second squared. And that comes out to 1.3 meters. Any questions about that? So here, if you have a snowboarder coasts on a smooth track that rises from one level to another, if the snowboarder's initial speed is 4 meters per second, they will just make it to the upper level and come to rest. With a slightly greater initial speed of 5 meters per second, the snowboarder is still moving to the right on the upper level. Is the snowboarder's final speed in this case 1 meter per second, 2 meters per second, or 3 meters per second? So I'll let you think about that for a while. Remember, energy is conserved. So you could find out how much potential energy is here using the first situation, and then plug that into the second situation to find out how much kinetic energy is left. So this is fairly straightforward. We can say V1 initial 1 is 4 meters per second, the final one is 0 meters per second. The initial 2 is 5 meters per second, the final 2 is a question mark. We don't know what delta U is, our change in potential energy, but we're going to need to know it to figure out V final 2. So E initial equals E final. So K initial plus U initial equals K final plus U final. So K initial minus K final equals U final minus U initial. So K initial minus K final equals delta U. So 1/2 MB initial 1 minus 1/2 MB final 1 equals delta U. And that's 1/2 M mass times 4 meters per second squared minus 0. That's delta U. So delta U is 1/2 mass times 4 meters per second squared. So if we think about this for the second case, K final equals K initial minus delta U. K final 2 minus K initial 2 minus delta equals K initial 2 minus delta U. So 1/2 MV final 2 equals, 1/2 MV final 2 squared equals 1/2 MV initial 2 squared minus 1/2 M times 4 meters per second squared. Well, now we can plug in the numbers we know. We know what V initial is, and we can divide everything by 1/2 mass. We can divide everything by 1/2 mass. We get V final squared equals V initial squared minus 4 meters per second squared. V final squared V initial squared is 5 meters per second squared, so V final squared equals 5 meters per second squared minus 4 meters per second squared. We take the square root of that, we get V final squared, and that is 3 meters per second. So basically, here we have 4 squared, 4 gets us to the top of the hill, so 4 squared gets us to the top of the hill. And so we have 5 squared minus 4 squared leaves us 3 squared. And that'll be our speed at the top. So now, energy conservation isn't limited to gravity. We can also involve spring. So we have the potential energy of a spring is 1/2 kx squared. So, in this situation, our initial state, we have some potential energy in the spring, we have some negative potential energy due to position, and no kinetic energy. And at the end, there's no potential energy in the spring, no potential energy due to the position, but we do have some kinetic energy. So the initial energy is U initial plus K initial, it's 1/2 KD squared minus MGD plus 0. The final is 0 plus 0 plus 1/2 MV final squared. If we set them equal to each other, we could find out what the velocity of that box is. So here we have a problem with the spring. We have a 17 kilogram block, 1.7 kilogram block sliding on a horizontal frictionless surface until it encounters a spring with a force constant of 955 newtons per meter. The block comes to rest after compressing the spring a distance of 4.6 centimeters. Find the initial speed of the block. So initially, you just have kinetic energy, and at the end, all that kinetic energy has been converted into potential energy of the spring. So our final law, that's initial. Typo, great. Just there. Oh, no. That was right. And I just overthunk myself. Yes, our final velocity is 0. We've come to a stop. Our mass is 1.7 kilograms. K is 9.55 newtons, 955 newtons per meter. Our X is 4.6 centimeters. Actually, it would be negative 4.6 centimeters. Oops. You know what? I'm going to leave it as positive. Oh, wait, no, this works. Negative. This is actually properly. Sorry, let me fix that. So our final velocity is 0, m is this, x is negative 4.6 centimeters, and initial velocity v is what we're trying to find. So energy initial equals energy final. K initial plus potential initial equals K final plus U final. So 1/2 mv initial squared plus 0, because there's 0 potential energy here, equals 0, because it's not moving, plus 1/2 kx squared. We can multiply both sides by 2 and divide by mass. So we divide both sides by 1/2 mass. We get v initial squared equals kx squared over n. We take the square root, we get v initial equals the square root of k over m times the absolute value of x. The sign goes away because it got squared and square rooted. So 955 newtons per meter over 1.7 kilograms equals minus 0.46 times minus 0.4, absolute value of minus 0.46 meters gives us 1.09 meters per second. In the image, x is negative, so I'm trying to be consistent. But the sign doesn't, it just gets erased by the squaring and square rooting. Any questions about this? Okay. So let's look at the same block, but instead of going horizontally, let's go vertically. So let's start with the block compressed 4.6 centimeters, mass at rest, and we want to see what velocity we'll have when the spring has returned to its equilibrium position. We're flinging the box off into space. We want to see how fast it's going when the spring has returned to equilibrium. So K, so I'll just give you the initial conditions because, you know, our initial velocity is 0 meters per second. Our mass is 1.7 kilograms. K is 955 newtons per meter. And X is negative 4.6 centimeters, or Y in this case. Actually, let me quickly freeze that and fix it real quick. That fixes it. And then unfreeze, and we're looking for our final velocity. I'll give you a little while over this. Now we'll move this out of the way. So here, when we work on energy, we'll have both gravity potential energy and spring potential energy. So it's helpful that we set our 0 to the 0 point for the spring. So we're using the same Y for both gravity and for the spring. So our initial energy equals our final energy. So that's kinetic energy initial plus gravitational potential energy initial plus spring potential energy initial equals kinetic energy final plus gravitational energy final plus spring energy final. So that's 0 plus mgy plus 1/2 ky squared equals 1/2 mv final squared plus 0 times 0. So solving for v finals, dividing everything by 1/2 mass, v final squared equals 2gy plus ky squared over m. So v final is going to be the square root of 2gy plus ky squared over m. So that'll be 2 times 9.81 meters per second squared. This is negative 0.0460 meters. So this is going to be a negative number. 955 meters per meter times negative 0.046 meters squared divided by 1.7 kilograms. So we have negative 0.9025 meters squared per second squared plus 1.189 meters squared per second squared, square root of 0.2862 meters squared per second squared. So V final is going to be 0.535 meters per second. Any questions about that? Just if you have multiple sources of potential energy, you have to take both into account. So, in the presence of non-conservative forces, the total mechanical energy is not conserved. So we were dealing with only conservative forces, then total mechanical energy is not conserved. However, it turns out the total work is the work done by conservative forces plus the work done by non-conservative forces. And that's minus delta U. That's the work done by conservative forces plus work non-conservative, and that equals delta K. So it turns out the work done by non-conservative forces is delta U plus delta K or delta E. So basically, energy final equals energy initial plus work non-conservative. You could have non-conservative work adding energy to the system, so the final energy could be higher, or you can have non-conservative work removing energy from the system. So here, for example, the non-conservative work is the resistance force of the snow. So you can see here, you start with some potential energy and zero kinetic energy. You plummet into the snow. You end up with some negative potential energy and again, zero kinetic energy. That non-conservative work was done by compressing and the snow and resisting that resistance force of the snow. So here in a forest, deep in the forest, a 17-gram leaf falls from a tree and drops straight to the ground. If its initial height was 5.3 meters and its speed just before landing was 1.3 meters per second, how much non-conservative work was done on the leaf? So, work non-conservative is equal to change in energy. So that's, change in potential energy plus change in kinetic, or, energy final minus energy initial. So all we need to do is find the final energy and the initial energy and take the difference. So our initial velocity is 0. Our mass is 0.017 kilogram. Our initial height is 5.3 meters. Our final velocity is 1.3 meters per second. Our final height is 0. So what's our non-conservative work? Well, non-conservative work is change in potential energy plus change in kinetic energy. So 0 minus mgh plus 1/2 mv final squared minus 0. You could also think of this as final energy minus initial energy, which would be 1/2 mv final squared minus mgh. 0 minus 1.7 times 9.8 meters per second squared times 5.3 meters plus 1/2 times 1.7 kilograms times 1.3 meters per second squared. We have negative 0.833 joules. That was our starting energy. Plus 0.0144 joules. So the non-conservative work was negative 0.869 joules. So friction, air resistance did a bunch of negative work on the way down. That is what you would expect. Here we have a skier who drops our 3.12 kilogram glove from rest at a height of 8 into fresh powder snow. The glove falls to a depth of 0.147 meters below the surface of the snow before coming to rest. If the non-conservative work done on the glove is minus 1.44 joules, what is the drop height of the glove? So here with this glove, our initial velocity is 0 meters per second. Our final velocity is 0 meters per second. The only energies involved will be potential. Our mass is 0.312 kilograms. The distance that it plunges into the snow is 0.147 meters. The non-conservative work done on the glove is minus 1.44 joules. And we want to figure out what the height it started at above was. So non-conservative work is change in potential energy plus change in kinetic energy. So that's our final potential energy, mg minus d minus mgh plus 1/2 mv final squared minus 1/2 mv initial squared. That is all zero, so this is just mg minus d minus h. So the non-conservative work over mg equals minus d minus h. So height is going to be minus non-conservative work over mg minus d. So minus 1.44 joules over 3.212 kilograms times 9.8 meters per second squared minus 1.47 meters. So the total height from top to bottom is 0.741 meters. And then we subtract 1.47 meters to find out how high we started above the snow. And so 7.4 meters. That looks wrong. Let me check my math. Yes, I typo. I transposed some numbers. It's 4.7, not 7.4. What you get when you type too fast. So these will be re-uploaded with all the minor corrections I've made. But it's 3.324 meters. So sorry about that typo. Yeah, so we have enough time. So here we have a golfer. Golfer badly misjudges a putt, sending a ball only 1/4 of the distance to the hole. The original putt gave the ball an initial speed of v initial. If the force of resistance due to the grass is constant, would an initial speed of 2v initial, 3v initial, or 4v initial be needed to get the ball to the hole from its initial position? So which of these would be required if your initial putt only covered 1/4 of the distance? So you need to go 4d to cover the whole distance. And that seems to be, no, it's just cropped wrong. Let's see if I can fix the cropping. There. So that mistake's been around for a while. So this is really basically just a work problem. Work non-conservative is equal to the change in potential energy plus change in kinetic energy. The height doesn't change, so there's no change in potential. So it's just change in kinetic. So the non-conservative work is minus 1/2 mv squared. So that's minus the resistance force times the distance is minus 1/2 mv initial times d is minus 1/2 mv initial squared. And then in our second case, the resistance force times 4d is minus 1/2 mv final squared. So 4 times a half. So if we pull out the 4, we have minus force resistance times d. We can replace that with minus 1/2 mv initial squared. And so we get 4 times 1/2 mv initial squared equals minus 4 times 1/2 mv initial squared equals minus 1/2 mv final squared. So 4v initial squared equals v final squared. So if we take the square root of both sides, we get 2v initial equals v final. You need twice the speed, because twice the speed gives you 4 times the initial kinetic energy, which will give you 4 times the distance. So 2 times the initial. Here we have a block of mass 1 at 2.4 kilograms. It's connected to a second block of mass 2, 1.8 kilograms, as shown in the sketch. When the blocks are released from rest, they move through a distance of 0.5 meters, at which point M2 hits the floor. Given that the coefficient of kinetic friction between M1 and the horizontal surface is 0.45, find the speed of the blocks just before our M2 lands. So remember that the force for kinetic friction is mu kinetic times the normal force. So I'll give you guys a few minutes to work on it. Our initial velocity is 0 meters per second. Our initial mass 1 is 2.4 kilograms, mass 2 is 1.8 kilograms. That distance it's going to fall is half a meter, 0.5 meters, and mu kinetic is 0.45. We need to find the final velocity, and for that we'll need to know what the non-conservative work is. Non-conservative work is change in potential energy plus change in kinetic energy. So that's minus force of friction times distance, which equals 0 minus M2 GD, because that would change in potential energy. It goes down by M2 GD. And the kinetic energy goes up by 1/2 mv squared plus 1/2 m2v squared, and 1v squared plus m2v squared. And our initial kinetic energy is 0. So if we plug in our formula for friction, that's mu kinetic times mass 1g, because that'll be the normal force, times d. That equals minus mass 2g times d, plus 1/2 mass 1v squared plus 1/2 mass 2v squared. So combining these, we get 1/2 mass 1 plus mass 2v squared. Then we move m2gd over to the other side. So minus mu kinetic m1gd plus m2gd. And then we divide everything by mass 1 plus mass 2. 1/2 mass 1 plus mass 2. Oh, I simplified it a little. I pulled out the g, mass 2 minus mu kinetic mass 1 times gd. So we have 2 mass 2 times mu kinetic mass 1 times gd over mass 1 plus mass 2. That equals v squared. So v is the square root of 2 mass 1 minus mu kinetic mass 1, mass 2 minus mu kinetic mass 1, gd, all divided by mass 1 plus mass 2. So 2 times 1.8 kilograms minus 0.45 times 2.4 kilograms times 9.8 meters per second squared times 0.5 meters divided by 1.8 kilograms plus 2.4 kilograms. And that comes out to 1.3 meters per second. Here we have an 80 kilogram jogger, starts from rest and runs uphill and into a stiff freeze. At the top of the hill, the jogger has done the work. Non-conservative 1 plus 1.8 times 10 to the 4 joules, and air resistance has done the work. Non-conservative 2 minus 4,420 joules. And the jogger's final speed is 5.3 meters per second. Find the height of the hill. So non-conservative work, change in potential energy plus change in kinetic energy. mgh minus 0 plus 1/2 mv squared minus 0 equals non-conservative work 1 plus non-conservative work 2. So non-conservative work 1 plus non-conservative work 2 minus 1/2 mv squared equals mgh. Divide everything by mg to find h. So if we, I screwed up the order of things. Mass is 80 kilograms. Non-conservative work 1 is 1.8 times 10 to the 4 joules. Non-conservative work 2 is minus 4,420 joules. Final velocity is 3.5 meters per second. We're looking for height. So the height equals 1.8 plus 1.8 times 10 to the 4 joules minus 4,420 joules minus 1/2 times 80 kilograms times 3.5 meters per second squared divided by 80 kilograms times 9.8 meters per second squared, which is 1,000 No, 13,090 joules divided by 784 newtons, or 16.7 meters. I screwed up the animation order on this. That should have been first. So that's non-conservative work. So potential energy, we can draw potential energy curves. It turns out the curve of a hill or a roller coaster is basically a plot of gravitational potential energy. So point A here and point D, you have the same potential energy because you're at the same height. As you dip down, your potential energy dips down. As you go back up, your potential energy goes back up. The potential energy curve for a spring is a parabola because it's 1/2 kx squared, or ki amplitude squared is E0, but it's 1/2 kx squared. And it will oscillate back and forth between those. Another thing that is basically a potential energy curve is a contour map. So this is a map of a mountain with contour lines. This is showing you the height. Height is basically potential energy. So here, we have a system that consists of an object moving along the x-axis, subjected to the potential energy curve shown here. The mechanical energy of this system is E up here. So rank the points A, B, C, and D in order of increasing kinetic energy and indicate ties where appropriate. So, which of these do you think has the lowest kinetic energy? Which of these points? A, B, C, and D. Which of them has the least kinetic energy? Remember, the total energy is going to be E, and the blue line represents potential energy. So, yep. Because A is the closest, it's the highest, it has the most potential energy, so it'll have the least kinetic energy. Kinetic energy is going to be the distance up to that dotted line. So lowest is kinetic energy of A. What do you think is next? Indeed, B is next. After that, yep, D is next, and then last is C. And that is the end of chapter 8. Conservative forces conserve mechanical energy. Non-conservative forces convert mechanical energy into other forms. Conservative force does zero work on any closed path, and the work done by a conservative force is independent of path. And some examples of conservative forces are gravity and springs. The work done by a non-conservative force on a closed path is not zero, and it depends on the path. Non-conservative forces are things like friction, air resistance, and tension. Energy in the form of potential energy can be converted to kinetic or other forms. And the work done by a conservative force is the negative of the change in potential energy. The potential energy of gravity is mgy. The potential energy of a spring is 1/2 kx squared, where x is how much it's stretched or compressed. Mechanical energy is the sum of kinetic and potential energies, and it's conserved in systems with purely conservative forces. Non-conservative forces change a system's mechanical energy, and that change is equal to the non-conservative work. So the work done by a non-conservative force equals change in the system's mechanical energy, and a potential energy curve is a curve of potential energy versus position. Now, I'm going to give you guys a choice. I haven't uploaded the slides for chapter 9 yet. Cause I'm almost done with them. And I just hadn't gotten around to, I didn't upload them early because I didn't expect to get there. We can either stop here today or we can start chapter 9. Which would you like? Okay, let's stop here. I have stuff I need to do. You guys, I think, have stuff you need to do. So I'm gonna stop here and I'm gonna